Welcome to Chapter 2, Unit 1. So Chapter 2 covers linear functions. Unit 1 covers linear functions. We're just going to start out. So first of all, you might ask, let me get a pen. What is a linear function? Well, that is a function that produces a graph that's just a line. And there's many ways, not a super whole lot, there's actually only 4. We can represent a function using words. We can represent a function using function notation. We can represent a function using a table, and we can represent a function using a graph. Function notation, again, that's f of x, things like that. A table, you have your x values, your y values. And a graph, you can have multiple types of linear graphs. So we're going to look at what a linear function is. So a linear function is a function whose graph is a line. Oh, if anybody's wondering why this particular video, maybe the slides look different than the book and the previous slides, is because I used the online version of the textbook, not the PDF. So they're the exact same thing, but for some reason they're just different colors. I think one's easier to read on the web and the other's easier to read as PDF, but it's the same. A linear function is a function whose graph is a line. Linear functions can be written in the slope-intercept form. Of course, your m is your slope, and your b is your y-intercept. So when x equals 0, your f of x is going to equal b. There we go. M is slope. There's multiple kinds of slope. We can go over an example. So use a linear function to find the pressure of a diver. The pressure in pounds per square inch of the diver. We're going to ignore figure 4 because it was just a picture of some diving lady, and I didn't really care enough to take it. So in pounds per square inch on the diver, so we'll have a diver here. Big flipper feet. And we'll give him a big yellow. Oh, we can't really see yellow. Give him gray. There's just tons of garbage going to their mouth, right? And things floating off divers. Anyway, so here's our diver. It's always interesting to draw a picture because math tends to be one of the more boring subjects. So here's our diver. And the pressure in pounds per square inch on this diver depends upon her depth below the water surface in feet. So it's going to depend on depth in feet and the pressure on her. And the pressure, kind of squeezing from all around. And the pressure is in PSI. The relationship is modeled by this equation. P of D equals 0.434D plus 14.696. So we're going to restate this function in words. Oh, this might be long. So if D is the depth below the water, we could start out with the pressure on a diver. D feet below the surface of the water. Oh no, we don't need that. Okay, the pressure on a diver D feet below the surface of the water is equal to 400 and 34 thousandths is equal to 434 thousandths times the depth plus in words 14 plus 14 and 600 and 96 thousandths. Oh, geez, okay, that was a lot. So the pressure on a diver D feet below the surface of the water is equal to 434 thousandths times the depth plus 14 and 696 thousandths. Of course, there's other ways you could rearrange those words, but this is my restating of the function in words. Now determining whether a linear function is increasing, decreasing, or constant. So remember our slope is our rate of change, so that's our rise over our run. So if our slope is greater than 0, that means we're going to have a positive slope. So we're going to be increasing as we move from negative infinity to infinity. So it could really be anything, like as long as the slope is positive. It could even be crazy positive. So if m is less than 0, that means our slope is negative. So as we're moving from negative infinity to positive infinity, we are decreasing in value. These are all negative. And when m equals 0, we just get the constant function y equals b. Because notice from here in this gray box, when f of x equals 0 times x plus b, you're going to get just b, because this cancels out. So no matter what x is, you're going to get b. Okay, so we're going to decide whether these functions are increasing, decreasing, or constant. So recent studies suggest that teenagers send an average of 60 texts per day. Wow, that's a lot, but I totally believe it. For each of the following scenarios, you're going to find the linear function that describes the relationship between the input value and the output value, And then we will determine whether the graph of the function is increasing, decreasing, or constant. Okay, 60 texts per day. Wow, okay. So A, the total number of texts a teen sends is considered a function of time in days. The input is the number of days and the output is the total number of texts sent. So if the input is days and it's 60 texts per day and we want the total number of texts sent, it's going to be 60D. Now, for B, a teen has a limit of 500 texts per month in his or her data plan. The input is the number of days. Number of days is the input, and the output is the total number of texts remaining for the month. So if you start out with 500 and you use 60 per day, on average, then this is what it would be for a month. Okay. A teen has an unlimited number of texts in his or her data plan for a cost of $50 per month. The input is the number of days, and the output is the total cost of texting each month. Well, it's unlimited, so it's 50. Okay, so we're going to first rearrange this one is negative 60D plus 500. So notice that's in the form y equals mx plus b, which is the same as f of x equals mx plus b. But since you have d, it's md plus b. So now that we can see that whatever number is in front of the d is going to be our slope, so here our m equals 60, which is greater than 0. So therefore it is increasing because it has a positive slope. Here, notice we have negative 60. That's less than 0. So it's decreasing. Notice here we don't have a d. So our m is equal to 0. It is constant. So calculating and interpreting slope. So remember, slope is rise over run. So your rise is your change in vertical height, and your run is your change in horizontal distance. So remember, that's the change in y, or the change in x. Now, slope can be interpreted as the units in vertical change given 1 unit in horizontal change. So, finding the population change from the linear function. So, suppose we had a function that gave us the population given the year, then our input would be a year and our output would be the population. So we can think of these as X and Y values. So in 2008, the population was 23,400. In 2012, the population was 27,800. I'm going to go ahead and delete this comma. There we go. Make it a little less confusing. Okay, and this says find the change of the population per year if we assume the change was constant from this year to this year. So if the population numbers are Y's, we're going to have 27,800 minus 23,400. And those are our Y values. And then we're going to do that over our change in X, which is 2012 minus 2008. So 27,800 minus the 23,400 is going to give us 4,400. We will get 4 on the bottom, so therefore we get 1,100. So what exactly is that? That is the population change per year. So the population increased by 1,100 each year. Writing the point slope form of a linear equation. So the point slope form of a linear equation, it's called point slope because you only need a point and the slope. Notice the 1 point and the slope. So if I were given the slope and a point of 1, 1, then you could say y minus 1, that's your y, equals half x minus 1. There's your x. And this would be point slope form. And you can actually take that to slope intercept form that we learned earlier. So y minus 1, we're going to add 1 so that it equals half x minus 1 plus 1, half x minus half plus 1 equals half x plus half. Let's see, minus, yep. Write the point slope form of an equation of a line with a slope of -2 that passes through the point -2, 2. So it's y minus y1 equals m, x minus x1, and this is the point slope form. So we're going to have y minus 2 equals, the slope is -2, x minus -2, so that's plus 2. So y minus 2. It's negative 2x minus 4. Then we add 2 to both sides. So we get, this is in point slope. So then we get negative 2x minus 2. This is in slope intercept. So writing the equation of a line using 2 points. X1, Y1, and X2, Y2. So notice that you have, we'll do the point slope. So you have your formula for M is this, right? So now we just put that in here. Equals y2 minus y1 divided by x squared minus x1. And that is the 2-point form. It's not common. When you get rid of this, you simplify it, it's the slope-intercept form. Or I'm sorry, it's the point-slope form, which you can then also simplify into the slope-intercept form. This is more or less just a formula way of thinking about it. So write the point-slope form of an equation of a line that passes through the points, negative 1, 3, and 0, 0. Then rewrite it in the slope-intercept form. So this is my x1, this is my y1, this is my x2, this is my y2, and we are going to say 0 minus 3 divided by 0 plus 1, because it's minus minus 1. That's the slope. Now notice if we would have made, if we would have switched these around so that this was x2 and this was y2 and this was x1 and this was y1, we would get 3 minus 0 divided by negative 1 minus 0, which is just negative 3 also. So it doesn't matter, but be consistent with your labeling. So we know this is our slope, and I'm going to pick this point. Yeah, make it difficult a little for you guys. So you're going to have y minus 3, and this is point slope form. Y minus 3 equals the slope times x minus x1, but it's minus minus 1, so it'll be plus 1. That's going to give us y equals negative 3x minus 3 plus 3. So it's going to be y equals negative 3x, and this is slope intercept. Now notice if we would have used the other point, we would have just gotten that almost immediately. So it's a little too easy for me to illustrate that one, so I went the other way. This is slope intercept. Writing and interpreting an equation for a linear function. Okay, I'm going to go ahead and stop here because I think this video is long enough. So I will see you in part 2.